Welcome back to our study of integral calculus, and today we will talk about the fundamental theorem of calculus. Fundamental, so it has a pretty highfalutin name, so you got to believe it must be thought to be important. What we've seen in 5.1 and 5.2, we've talked about the definite integral, and we've talked about area under the curve, right? So we've developed this kind of notation. We were doing these kind of problems like from 0 to 10, f of x dx. And we were adding up perhaps this area right here between 0 and 10. And we might have called that this area under the curve. Okay, so why was this fundamental? Well, they had one camp of mathematicians was figuring out how to compute these areas, and then you had other guys working on rates of change that were taking the derivative of other functions. Let's call it this, taking derivatives of functions. Okay, so we have the guys taking derivatives and guys taking integrals. These guys were interested in rates of change. These guys were adding up little changes. They didn't realize they were kind of working on the same problem, and these processes were inverses of each other. So the fundamental theorem of calculus is going to unite these guys, and it's going to show them how a derivative and how an integral are related. And once you do that in any field, once you show one field is like an other, then you can bring all these tools together, bring the power of kind of collaboration between the groups. So in one book I used to use, it said this theorem, when they figured this out, this sparked the technological revolution for the next 200 years. Kind of amazing statement. Now we're just going to use this. It's going to be rules that we use, and you're not going to be that impressed by it. But you have to put yourself back in the perspective before they knew this. Okay, well, let's get started. Okay, in a homework problem you worked last night, you were asked to figure out what these definite integrals were, okay? And you calculated the area under the curve from 0 to 14, which I guess, what is this, 12 here, so these are 6, so I guess that was that. You were basically finding out the area under the curve here, and you said that was 196. You went out to 35, and you said that was 490. Okay, when you went 0 to 63, you said that was 98. Some other properties of it, what would you say this was? I'd say if I integrate from 0 to 0 of f of x dx, you could say that's equal to, well, that's one of the properties of the integral, that's 0. So you see, if I plug in different values here, I get different answers. And I want to give you some notation that might scare you at first, but let's write this as a function, okay? I could actually say g of t is equal to, I'm going to integrate from 0 to t of f of x dx. Okay, so I've created a function here, right? I put in a t, so this first time here, t was 14. Okay, t is equal to 14. If I'm talking about this t is equal to 35, 63, or 0. So we could say g of 0 is equal to 196. Oh, I'm sorry. The phone's ringing here. I'll be right. Okay, back. Hopefully the phone won't ring again. If I put in a 0 here, right, that's the same thing as saying that's going to be 0, right? That's from over here. G of 14. Well, g of 14 then is what? Let's just write it down. 0 to 14 of f of x dx. That's equal to 196. And so on. G of 35, I think you see the pattern here, is equal to 490. G of 63 is equal to 98. So, I mean, I could plot this. I could plot this as a function now. What does a function do? It takes in an input value, gives me an output. So if I wanted to plot this here in red, the scale's different, okay, but at, see if I can do, at 0, it's equal to 0. At what? At 14, it's equal to 196, and we'll say this is 196. Sorry, this is going to be on a different scale. 196. And at 35, which is, that's 12, 24, 35 here, we'll say that's equal to about 490, which we'll say is a little bit off our scale. And then at 63, what is this? 12, 24, 36, 48. 48. Might have my scale a little wrong here, but we're going to, you'll get the idea that I could create a function. And I don't know, actually I do know something about that. It's going to be a max, like that, okay? And this could be g of t. So g of t is a function, and I just want you to get used to this kind of notation. I'm going to write the integral of f of x, and what is this? This happens to be from 0 to t is basically, I'd say this. I'm going to integrate this thing up to t, okay? So I'm going to integrate from 0 to t. The area under the curve is going to be g of t, okay? Okay, once you get the idea that you have you can write the integral as a function, I could say, well, g of t is equal to 0 to t, 0 to t, f of x dx, okay? These are my endpoints. This is x equal to 0, x equal to t. I'm going to write this and say and give you a little vocabulary and then go back and tell you what it is. I'm going to say that's equal to the big cap F, the antiderivative at x, evaluated at t and 0. What's this called? I'll write this, and then I'm going, what's this t and 0 notation? This is the big cap f of t minus big cap f at 0. What is this thing called? This is called the antiderivative. The inverse of the derivative. Derivative. Okay, we're going to have to talk a lot more about what an antiderivative is, but it's just another function. Another function has to be the antiderivative at f. Okay? Notice g of t is a function of that. This is just a number here. This is just the antiderivative evaluated at 0. Okay, now what they're going to call the first, we'll call the, what's the thing? The first part of the fundamental theorem. Such a highfalutin name. The first part of the fundamental theorem of calc. Okay, I don't want to write that out too much. Well, this is a function, right? This is a function of t. Well, if it's a function, I have to be able to take a derivative. And what is it? If I took the derivative of g of t, it's a function of t, right? So if I took that thing with respect to t, it's going to be f at t. Okay? It's going to be, notice, this same, I'm going to get back, let's try that again here. I've integrated little cap f of x. I integrate it, I get this antiderivative, it's equal to this. When I take the derivative, I get back where I started from. Okay? That's the fundamental theorem. Now notice, let's write this again. Well, what's g of t equal to? Well, g of t, I said up here, is equal to this. It's equal to big cap f of t minus big cap f of 0. Okay, well, let's take the derivative of that. What's the derivative of g of t? And I can take the derivative of both sides here, right? And I'd say, well, the derivative of big cap f of t dt minus, what's the derivative? This is a constant. So this is just 0. Okay, so let's change the notation. G prime of t is equal to f prime of t, right? The derivative of that. And that's equal to what? Well, the fundamental theorem says that's f of t. That's f of t, okay? So what is the antiderivative? The antiderivative is something that if I take the derivative of the antiderivative, so if I, it's like a minus of a minus, if I take a derivative of an antiderivative, I get back to where I started, and that's what this says. If I take a derivative of an antiderivative, I get back to the original function. Okay, let me give you a little picture of that. That is the first part of the fundamental theorem. Maybe here's my little picture. I don't know if this helps at all. I can take a function f of x, and I can shove it through an integral operator. Okay, I can integrate it left to right. And when I do that, I get a g of x. Say I get a g of x. When I put the g of x through a derivative operator, if I take a derivative of it, what do I get back? I get back to where I started from. Okay? So these are, we might say these are inverses of each other. Inverses. So you see the relationship? The guys that were doing integration and the guys that were doing differentiation were doing inverses of each other. If you take the derivative of a function you got when you integrated this function, you're going to get back to the original function. That's what this is saying. That's what united these two camps, the derivative guys and the integral guys. Okay, we're going to have a lot more to say about that. And I'll finish this up and then start a second video. Okay, the second part of the theorem I've already given to you, basically, but I'll write it down again. And that's how do you evaluate an integral? How you evaluate an integral with an antiderivative. We're going to say the following. If we integrate from a to b, f of x dx, that's the same thing as getting the antiderivative. Evaluated from a to b, here's a notation. It's going to be the antiderivative evaluated at b minus the antiderivative evaluated at a. We will use this all the time to calculate integrals. Now the question is, well, how do we find the antiderivative? Well, this was in 4.9 and we didn't do it. Now we're going to talk about it because we're going to need it. We're going to need that section now. And let's just remember a few things. If we take, this is the basic thing, if we take the derivative of f of x with respect to x, we got to get back to what we started with. Okay, so this is the property we're looking at. Let's see if we can figure out what antiderivatives are. What if, what's the antiderivative if we're integrating x dx? Okay, let me try that again. Let's put different f of x's over here. F of x, we'll put f of x here. Let's take some examples. What if it's x? We need to, well, then what's then, if it's equal to x, what's the antiderivative? Well, I'm going to tell you what. Let's see if you get this. I'm going to say that's equal to x squared over 2. How do I know it's x squared over 2? Well, what is the derivative? The derivative of f of x dx. You can take derivatives, right? Well, that's going to be 2 times x to the first power over 2. Well, that's just x. Okay, so can you see we got back, we've satisfied. We took the derivative of the antiderivative and we got back to what we started from. Okay, that looks pretty promising. Shall we try another one? What if we let f of x, what about x squared? Well, what do you think f of x is? You might think about, well, what do I have to, if I'm taking a derivative? You can start thinking about taking a derivative of something. If I want to get an x squared term, I'm going to have to start with an x cubed term, right? Okay, so maybe it's x cubed, but when I take a derivative of x cubed, I put a 3 down in front. Oh, I got to cancel that out, so I got to put a 3 underneath here. Does it work? Well, here, I'll just write the notation. I'll say, what's the derivative of the antiderivative? It's 3x squared over 3 is equal to x squared. Check. It seems to work. This must be the antiderivative. What if let's try one in general. What about f of x equal to x to the n? X to the n, okay? What do you think f of x is equal to? Well, it's got to be x to the n plus 1, right? It's got to be x to the n plus 1. We better not get these confused here. Whoa, look at that. We'll change colors on you in the middle. It's got to be x to the n plus 1, but then I gotta compensate for that factor coming out in front. Does that work? Well, let's try. What's the derivative of this? It's equal to, I bring the n plus 1 down in front, x to the n over n plus 1. Oh, sure enough, those cancel. It's equal to x to the n. Okay, so you see I got a rule. If f of x is equal to that, the antiderivative is, that's the inverse of the power rule. It's kind of going the other way, the antiderivative. Okay, I think we got a pretty long video here. We better cut this one short and make a second one. See you soon. Bye-bye.